Hello guys, today I am using Matlab in order to solve some ordinary differential equations. So I will choose one question or one example and I will try to solve it by Matlab. So let's see this equation, which is second order ordinary differential equations. And we have non-homogeneous part, and also we have two initial conditions. So just open Matlab and try to save the script into your home directory. So let's choose desktop and write the title of the script. I will write general solution for ODE, and I'm gonna save it on the desktop. And also I will write CLC, clear all. The purpose of those to clear up the history of Matlab. So if we want to interpret these equations into Matlab, all you have to do is to write some sample for the ODE equals to the second derivative. How can I write the second derivative? Well, from this definition, y in terms of x, 2, that means the second derivative. And I have here plus 4 times first derivative. So plus 4 times first derivative plus 4y plus 4y equals here double equal. Since I have 1 here, so I have to make it here double. All right. Exponential function for 2 times x times sine 2 times x. And I can close the statement of Matlab by putting semicolon. All right. So this is ODE. How about the conditions? Well, I can write CO, the condition 1, when y equals something for x0. So it is 1. It is 1. Condition 2, the derivative of y when x equals 0, it is minus 1.5 and semicolon. But here I have to find something at the beginning, and these things will be system, or the abbreviation for system, y in terms of x, all right, and the first derivative will be like that. So now I have everything set up, the ODE, the conditions, and everything is defined here. All right. All you have to do is to find a solver. In Matlab, we have many solvers. So I'm gonna choose dsolve command to find the general solution and the particular solution. So let's see general solution. General solution, dsolve. Since I have these between the parentheses, that means my command is correct. So I am solving for ODE, for this ODE. So let me check. So here I have to put some additional equal, since I have the first one here. So let me see. I got the general solution in terms of C1 and C2. In order to find a particular solution, well, just input the initial conditions. So ODE plus the conditions. Here I have two conditions, so let me combine them by this command, conditions, and doing factor, condition 1, condition 2. So this is the sign of factor. These parentheses means the conditions are factor, condition 1 and condition 2. So let me write the exact name here as it appears here. So now this one should give me, I want to close this one and open this one to give me the particular solution at these conditions, two conditions. So now I have some equation for the result. I mean, in the analytical solution, I got the general solution. So let me compare them, the solution of Matlab with the solution of the analytical one. Before that, let me do some simplifying. So the particular solution will be simplify ODE or BS. So here the two solutions are identical. That means our analytical solution is correct, since everything here in Matlab is also correct. So both give the same solution. Thank you. Hello everybody. Today I'm gonna use Matlab in order to solve this equation numerically by using Euler method, modified Euler method, Hewens method or improved Euler method, and also branch-Cotta method. So I have this ODE, I have the initial condition, and there are some information here about the numerical solution. The T final 10 seconds, N number of discretization N, 100, 1000, and also calculate the residual of the three approximations with respect to the exact solution. So let's begin this by opening this new script for Matlab and save as this script in our home directory, let's say desktop. And let's title this. This is a numerical particular solution. And let's begin recording by writing CLC and clearing out all the history of Matlab. So we are making the new one. How I write this equation into Matlab? Well, there are some definitions in Matlab in order to define a function. So I'm gonna use that with inline defining. So let's name the derivative f at y and t. The rest I will take it from here. Cosine t minus 2 times y. So this is the definition for this equation into Matlab. All right. And also, in order to find h or the increment, t final equals to 10 semicolon, and the first n is 10. So that means h tf over over n. So as long as I increase n, that means I am getting tiny h. And we know if h is very small, that means the approximation is very accurate, or it's accurate, and it's close to the exact solution, as we will see. So here in the beginning of Matlab, I got f, I got h, or delta t, which is required if you look at the three forms. The first form, Euler, we should write delta t or h and f. So I got them here. All right. Well, since I have a vector for y and t, so let's do the bases and make the bases zeros. So y equal zeros for the dimension of this vector, one row, and the column will be always 1 degree over n. Okay, it's the same for t. 1. So I just giving zeros to the positions of these factors of so y and t. So let's look at the form again. Since I have n plus 1, and that means I have series. So in Matlab, I will write for I equal 1 to n. Y I plus 1 equal to yi, see, yn plus 1, here I, since we have iteration and the end n, plus, instead of delta t, let's write h, and here we have the function f. In order to evaluate f, evaluate, here is the command in Matlab. So I'm gonna write this f, which is this function, and since I have here y and t, so let's write y and t in the same order. So here two values are substituted into f in order to find this term. All right, and let's close this loop, and also here let's define the system for y in terms of t. So everything here is complete now, except t starts from 0 with an increment h and reaches tf. So this is because I know the abscissa, I know the x-axis, which is d, from 0 to tf. And let's close this also statement. So see, now We have this function and we have this function, but let's name this, since we are using Euler, so let's name this YE. So substitute this YE and T into F, and by doing some summations. And by the way, this is the first value of YE. So I should give the initial condition when I equals 1, which is 0 from the equation itself. If we look at the example, we will find the initial condition is 0. So now everything should be correct, and in order to see the results, let's plot T with respect to YE. And here YE, Euler. All right, and let's close this also semicolon. So now let's run it and see the result. So here the first solution by Euler when n equals 10. See, if I increase n, that means we have a smaller h. So I should get something more smoother than the first one. If I make it even better, I will get also much smaller or smoother than the first one. So this is the solution, approximate solution. Why? Because I am using numerical method. If I want to compare the numerical method with the exact solution, so I have to write the equation for the exact solution, which I have already here. In this example, I have the exact solution. So let's compare it and see whether our solution is correct or not. This is the particular solution at the initial condition. So 1/5 sine t plus 2/5 cosine t minus 2/5 exponential plus 2/5 cosine t minus 2/5 exponential So it's correct. All right. So this is the particular solution, and we have the vector t will be substituted by this vector, and in order to compare the two results, let's hold on the same figure and plot t with respect to particular solution. And let's name this or make it obvious by the color black. This is black, and this let's make it blue, and see whether our see there's a little difference between the two solutions. So our numerical method it's accurate. It's accurate enough in engineering. But if I make this small, we will see there are a lot of differences between the two solutions. So this solution when n equals 10 is not accurate. So imagine if we do this by hand for three steps. If we do this by hand for 3 steps, oh, this is wrong. So this solution is wrong. So always in numerical method, it's preferred to do it by computer and make this a reasonable value. Yeah, it's there is some error between the exact solution, black one, and the approximate solution, blue one, but should be fine. Should be fine. And yeah, so this form for Euler method. Okay, but now if I want to use and compare other methods like modified, so I should write some additional statements. So let's see that. For example, the modified Euler method, I have predictor and corrector, so K1, K2. This is the form. Let's close this figure and let's copy these statements, and so that will be for modified Euler, modified Euler, modified Euler, modified Euler, modified Euler. But here there is K1, K2. Okay. Let's relax our eyes. Okay. So here these are the three statements for modified Euler method. So K1, it's H or delta T times F. So I'm gonna copy or cut this one and make it here. K2 K2 H or delta T times F. Well, F here is not explicit, so should be some improvement here. Plus K1 and N minus, so N plus 1. Now should be okay. And finally, the general form for Y. Let's remove H and write half times K1 plus K2. So K1 here, K2 here, we got everything set up. All right, so everything is correct. So for modified Euler method, let's plot this also with some distinguish. Modified Euler method. Let's make it green, for example, and see what is the differences between Euler and modified Euler, if there is differences. All right. So here we have a lot of differences when 10 equals yeah, when n equals 100. So the three methods, I mean, two of them are approximate, but there is some differences or errors between the two solutions. This one for the exact solution, and this green one for modified. And it seems we have also the blue one here. So there is some differences between Euler and modified Euler in this way with respect to the exact solution. All right. So let's remove this for a little while and see. Maybe hold on should be written before. Yes. So even for 100, I have some differences between Euler, the blue one, and the modified Euler. I mean the solution of these two methods. With respect to the exact solution, which one is better? So let's see. All right. So it seems the modified Euler method is closer to the exact solution rather than the blue one, the solution by Euler method. So now we see that the modified Euler method gives an accurate solution. So let's repeat this also for another form, improved Euler method. All right. Let's do it together. Let's copy and paste here improved Euler for units H. Let's see what should we change. The first or K1 is correct. It's similar. K2, however, has some factors. 2/3 times K1, and here minus or plus 2/3 times H. And the general form for Y, instead of 2, 4, K1 times 3 K2. Did I change the right one? Yeah, I did some mistake. I changed this one, but however, so this will be for for improved Euler method. Okay, and this will be for modified Euler method. Um, and also let's make another graph for h, and let's give red. So see, I wrote just the forms which are available here into Matlab, and did some modifications in order to match Matlab codes. So in this way, now everything should be correct. So let's watch together. Do I have red one? Yes. So see, still there are some errors between the red one, the green one, and the exact solution. But the red one seems now closer to the exact solution. That means YH improved Euler method is better than modified Euler method, and both are better than Euler method. So let's close this program with range cutter, which is preferable since it's fourth order and should be much higher in accuracy. So I will make this range cutter, RK, 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 and let's so K1 for range cutter. Where is range cutter? K1 it's similar. K2 K2Y here half, and here also uh, we have plus H. Too much this one. K3 K3 here also the same thing with K2, so nothing to change. K4, let's see K4, H, F, so here should be K3, same here, K2, should be K2, and N times 1, so let's here should be H here, so I should write something here. I think it's said here. Let's check this. So here plus H, K4. So I got here plus K1. Here should be plus H. All right. So K4, K3 times without n plus 1. So without plus 1. Yeah, some error we have here. Anyway, so K4, it's Tn plus h, not half h. And the general form of y will be 6 here, K1, 2 times K2 plus 2 times K3 plus K4. Let me check it again. K1, 2, 3, K4, K4 here, K2, good, K3 and K2. So 1 in terms of the previous one. K1 here, K1 here, K2 here, K2, K3 and so on. So now I can also add another plot and name it RK, which should be better than those three methods in terms of the solution, and make it yellow, for example. All right. If I wrote this correctly, I would get so the yellow one. Do we have the yellow one here? Oh, something wrong here. So let's close these things and see what is wrong with the range cutter. So the solution is done by range cutter. If I compare it with the exact solution, I should get something accurate, right? So the error between the approximate solution and the exact solution should be very small if I am using range cutter. So this is for future. Always use range cutter for your calculation. Yeah, so let's make it more distinguished. Another color. Let's see. Let's make it. Oh, yes. See, so the differences between the approximate solution and the exact solution are very small if I am using range cutter. If I am using other methods to get the general solution, the difference may be high. It depends on the n, it depends on how much discretization I have. So see, there are some differences, but still the order of the accuracy range cutter is better than improved Euler method. Improved Euler method is better than modified Euler method, and all are better than the first one, Euler method. So this is the idea of the numerical solution. The idea of the numerical solution is to get y here, y in terms of t. T will be discretized into some portions, from the initial condition 0 to the final, here the T final. So the idea says if the number of discretization is not good, like 10, I get like this equation solution. But still here, still range quota is better than others. Okay? And so at the end of this video, I'm gonna use also, there are some ready packages into Matlab which can be used in order to get the numerical solution for any ODE. So let's do this. In the initial condition, y not equals 0. The factor t and time, let's name it here t1 and y1. And the command for ODE for non-stiff equation 45. And here I need this function. I need this function. I'm gonna write it here and make this 1, make this 1. Let's see, let's change the order. Here T1, Y1, T1, Y1. And here T-span. Close this one. T-span the same here. It starts from 0 and ends at T final. And the initial condition, y. Let's close. Okay. So if everything is correct here, I am evaluating the numerical solution of this ODE with this initial condition and this interval for t by using this command ODE 45, which is for non-stiff ODE. So let's write another plot here. T1 and make this one, for example, star. So let's see. See these stars? These stars are even better than the solution of a range quota. So now we have these numerical methods, and we have the exact solution, and we have the package or built-in command in Matlab. 45, sometimes for stiff, if I have stiff ODE, that means I want a very tiny h in order to get stability, otherwise it's not stable. So it seems here is stable. Why? Because there is no error here. So even with the n here, it's stable. Let's make it 2 and see. Still something here. Anyway, so I got the solution for this function y in terms of t, and this should be the general solution for this example, and the analytical solution is done here also. If this is the exact solution, analytically, and these are the numerical solutions plus the exact solution. Thank you for your listening.